Okay, here we are back for our Wednesday lesson. I may have overdone it coming into school on Tuesday a little bit, so I thought I needed to rest my ankle another day. But hopefully things will go well with the video. You notice I have switched to black ink for my notes, and it does show up better on the camera, so hopefully that won't be a problem anymore. And we're picking up where we left off last time. Remember, section 15.5. I started that and I didn't really have any notes written, so I just had to make up an example from memory to sort of introduce the subject. And we went over that last time, so I won't go over it again. But excuse me. All right, I'm done with that now. To sort of elaborate on the idea in a little more detail. One of the things that you might want to use one of these ICE tables for, and remember ICE stands for initial, change, and equilibrium. One of the things you might want to use those tables for would be finding K from initial concentrations. Like the example I showed before, where you've got a reaction and you know the initial concentrations for everything, but you only know the equilibrium concentrations for one thing. Well, you can use that information to figure out the equilibrium concentrations for everything else. And once you have those, you can find the equilibrium constant. Okay, a simple example that the book uses is hydrogen and iodine forming hydrogen iodide. So H2 plus I2 going to 2HI. And it sets it up as if 0.5 moles of H2 and 0.5 moles of I2 react at high temperature and constant volume, and they mention 1 liter as the volume, and the amount of HI at equilibrium concentration of the product is 0.9 moles. What is the KEQ? And in a situation like this, you would want to set up an ICE table. Some of the examples are actually so simple that you can do them in your head once you get a little experience. But for the most part, you're going to want to set up an ICE table when you're first doing it. And I'm going to erase the answers that I wrote in yesterday and write them in as we go through the examples. So I'm starting out here just with what we know at the very beginning of the problem. We know that the initial concentration of HI is 0.5. And keep in mind here that you, for an equilibrium constant, you want to use either concentrations or partial pressures. And in this case, they said there was 0.5 moles of each reactant, but the total volume was 1 liter. So that means 0.5 molar is the concentration for each of these. So if they do give you a volume, go ahead and divide the number of moles by the volume so that you get molarity. And if they don't mention you starting off with any of the product, and they didn't in this case, you can assume that the initial concentration of the product is 0. And so that's why I wrote assumed after 0. Now, we don't know yet what the changes are, but one other piece of information they did give us was that the equilibrium concentration of the HI is 0.9 molar, or 0.9 moles in 1 liter, in other words. Okay, so here, but notice what we've got here with the HI. We know we started with nothing, and we know we ended up with 0.9 molar. If you start out with no product at all and you end up with some product, then of course the change was positive. And from 0 to 0.9, well, that change is obviously 0.9. It's going to be the final minus initial will be the change. And so 0.900 would be the change. That is equal to 2x, though, because of that 2 right there. Okay, so 0.9 is 2x. What that means is x is 0.45. 0.9 divided by 2. And so with the reactants, first of all, the change in the reactants is going to be negative because we started off with no product at all. So this reaction is clearly going to be going from left to right. You're gaining product and you're going to be losing reactant. And according to the stoichiometry, you're going to be losing x for H2 because the coefficient is 1. And you're going to be losing x for I2 because the coefficient there is also 1. And we just saw x is 0.450. Okay. And then to find these equilibrium concentrations for the reactants, you just take the initial plus the change. So 0.5 plus the change, which is negative 0.45, and you get 0.05 for the concentration at equilibrium of both of the reactants. One thing to watch out for here is, of course, concentrations, whether they're initial or equilibrium, have to be positive. So if you end up with a negative concentration in the first line or the third line of one of these tables, that's bad news. Change in concentration, though, can definitely be negative, because that's essentially what's going to happen. On one side of the equation, you're going to have a negative change, and on the other side, you're going to have a positive change, like we did here, positive on the product side and negative on the reactant side. Okay, so that's okay, but the first and third lines should always come out positive. Okay, so we can find the KEQ. It's just going to be the HI concentration at equilibrium squared, because of the coefficient of the 2, divided by the concentration at equilibrium of H2 times the equilibrium concentration of I2. So that's going to be 0.9 squared divided by 0.05 times 0.05, and that gives us an equilibrium constant of 324. So there's your KEQ. Problems like this occur quite often in acid-base type situations, especially like we saw in the lab, where the dissociation of a weak acid is, and actually I'm going to stop there because there's a problem coming up a little bit later that involves exactly that. So I'm not going to waste time talking about it now. So we'll come back to that later, though. Something in the table, you can also use units of numbers of moles or millimoles if you want, but that if you do that, that's kind of risky, because you would then be tempted to put those numbers into the expression for KEQ, and the KEQ expression requires molarity or partial pressure, not numbers of moles. So that's, so you got to watch out for that. An example that the book throws at us is carbon monoxide plus water is in equilibrium with hydrogen and carbon dioxide. And it says if 0.00925 moles of carbon monoxide and 0.0200 moles of H2O are in a 0.5 liter flask and allowed to equilibrate, and you come back later, once it's, once everything has had time to come to equilibrium, and you find that you've got 0.00825 moles of CO2, what is the KC? Well, this is an example that's very similar to what we just did. We know that the initial carbon monoxide concentration, and I think it's safe to change the concentration before setting up the table, is going to be 0.00925 moles divided by the volume, which is 0.5 liters. And that will be, 0.0185 molar. And the H2O initial concentration, and I like to put the little I after the brackets just to remind myself that these are initial concentrations, not equilibrium, will be 0.04 molar. And then they gave us the CO2 concentration at equilibrium, so I put the little EQ after the brackets, and that turns out to be 0.0165 molar. So we set up the table, and we set it up same as we did before for the previous example. So the initial concentrations for carbon monoxide and H2O would be 0.0185 and 0.0400 respectively. And the concentrations of the products, again, since they didn't mention anything about products at the beginning of this process, we can assume that there were no products there at all to begin with. So those are both 0. Now they tell us that the CO2 concentration at the very end, or at equilibrium that is 0.0165 molar, or rather this number of moles in 0.5 liters. And that makes 0.0165 molar. Well, by the stoichiometry of the reaction, that will be X, because all of the coefficients here are X. So 0.0165 is X. If you're gaining this product, then you're also gaining the other product. And since it's a 1-to-1 ratio, you should gain the same amount of the other product. So the H2 concentration at equilibrium will also be 0.0165. For the reactants, you're going to be losing concentration. But again, since everything is 1-to-1, that just means that you're losing 0.0165 molar concentration of H2O, which leaves you with 0.0235 molar. And you're losing the same concentration of carbon monoxide, which leaves you with 0.00200. And then KEQ is just products over reactants using, again, the equilibrium concentrations. So that's going to be 0.0165 times itself, because H2 and CO2 at equilibrium are the same, divided by 0.002 times 0.0235. And that gives us 5.798 as our KEQ. Okay, so that's not too difficult. So if you're trying to find equilibrium concentrations from the initial concentrations, and suppose in this case, and this is where it gets fun, suppose in this case you know the initial concentrations and you know KEQ, but you don't know any of the equilibrium concentrations. Then what do? Well, you can still find the equilibrium concentrations, but it may involve a little bit of difficulty. All right. So the example that the book uses actually is that same reaction we just did again. Carbon monoxide plus water is in equilibrium with hydrogen and carbon dioxide. And using the same reaction at the same temperature, but so the KEQ should be the same as what we found just now, but we're using different initial concentrations. So the equilibrium concentrations will end up being different, but the ratio of the products to the reactants will still come out to 5.8 like it did just a moment ago. So now we're using initial carbon monoxide concentration of 0.0125 molar. And for H2O, the initial concentration is going to be also 0.0125. And we're starting with no products at all. So those are both 0. Okay, so the first thing we need to do in a case like this, and actually in a case like this, is pretty obvious which way the reaction runs, because we're starting with nothing on the product side. So obviously it's going to have to run from left to right to create some products before it can come to equilibrium. But the way that you would tell if it weren't clear, like if we had numbers here instead of zeros, the way you would tell which way the reaction goes is to find Q with the initial concentrations. And that's just, or again, it's set up exactly the same as you would set up the equilibrium constant expression, except you don't know whether the concentrations are going to be at equilibrium or not. So the initial concentrations of H2 and CO2 are both 0, and CO and H2O are both 0.0125s, and obviously this is 0. And that means Q is less than KEQ, because remember KEQ is 5.8. Okay, and since Q is less than KEQ, the reaction goes to the right or forward, so that you'll lose reactants and gain products. That will bring eventually the value of Q up to 5.8, and then you'll be at equilibrium. So now we can set up the ICE table, and we have our initial concentrations on the top row. And now we go directly to the changes, since we don't know anything from the bottom row yet. And we can look at the, at the stoichiometry of the reaction. And since everything is 1-to-1, it's either going to be plus X or minus X for each of the entries in the change row. Again, the reaction's running left to right, so we're going to be losing reactants. So that's minus X and minus X. And we're going to be gaining products. So it's plus X and plus X. And so the final or equilibrium concentration for CO is just going to be initial plus change. And in this case, that's 0.0125 plus minus x, or in other words, 0.0125 minus x. And the same for H2O. And for H2, it's going to be, nothing plus x, which is x, and the same for CO2. So here are your equilibrium concentrations. The one little catch, of course, is that all of these concentrations involve x, and we don't know what x is. This is where the fun part comes in. We can put the x's, or the x involving terms, in the expression for KEQ, in which case we ultimately come up with KEQ, that is 5.8, is equal to x over 0.0152x, the whole thing squared. And we can take the square root of each side to get the square root of 5.8, which is 2.41, is equal to 0.0125, or x over 0.0125. So you notice it's not squared anymore. And we can get the x's on one side of the equation and the numbers on the other. And we end up with, say, 2.41 times the denominator of the right-hand side equals what's left of the right-hand side, which is x. And we multiply that out, we get 0.0301 minus 2.41x equals x. And again, bring the x's both over to the right-hand side. So we get 0.0301 over 3.41, because notice on the right-hand side, we're going to have x plus 2.41x. So that's 3.41x. So you divide both sides by 3.41, and we get 0.00803. Oh, sorry, 0.00883. Is x. And so that means the equilibrium concentration of carbon monoxide will be 0.0125 minus that, which comes out to 0.00367. H2O will be the same thing. And H2 and CO2 are both just x at equilibrium, so that's 0.00883 for each of them. Okay, so now we have the equilibrium concentrations, and we were supposed to find the KEQ for this reaction. Of course, we already knew it, but we'll want to check anyway, just to make sure that we get the KEQ that we should. And in fact, we do. If you take, 0.00883 times itself over 0.00367 times itself, you get 5.79, which is the KEQ that we found before. So we found x correctly. Now, that was the easy way to find x, because we ended up being able to take the square root of the side of the equation that had x in it. And so we ended up with x, but no x squareds. Unfortunately, the way these problems work out, very often you will have a progression of x's. You'll end up with something times x squared plus something times x plus something times x to the 0 power, which is just a number, because x to the 0 power is just 1. And that will be equal to 0. And that is a quadratic equation, meaning that you may end up having to use the quadratic formula if you want the answer to that question. The quadratic formula, if you remember, it is x equals negative b plus or minus b squared minus 4ac over 2a. And you always get two values for x. And in a problem like this, only one of those numbers will be correct. So you have to basically look at those two numbers and see which one works out and which one doesn't. Usually what will happen is that one of those numbers, when you put it into the formulas like we had in the ICE table, like 0.0125 minus x, a lot of times you'll have a value of x from the quadratic formula that will give you a negative number when you do that. And of course, you can't have a negative equation. So if x does that, that's the wrong value of x. Use the other one. X itself could be positive or negative. It's what happens when you put x into the equations in the ICE table and you get your equilibrium concentrations that will really tell you which value of x is reasonable and which one isn't. Sometimes one of the x's might turn out to be 0. And in that case, that's obvious. Well, x could be 0. There could be no change, I suppose. Fortunately, and this is common in most general chemistry 2 classes, I'm not going to give you any questions that require you to use the quadratic formula because that's math, that's not chemistry, and it takes an inordinate amount of time that you're basically working on math and not chemistry. And so you may get, I can't actually make any promises for the homework. The homework might throw you a question or two that requires the quadratic formula, but I will not. There are ways around the quadratic formula. One of them is to get a problem like the one we just did, where you can take the square root of both sides and end up with just x to the first power and just group the x's together and solve for x. And that's pretty easy. And the other case would be a lot of times you'll get a problem that appears to require the quadratic equation. But if the concentrations and the equilibrium constant relate in a certain way, then you can actually make certain assumptions that will allow you to avoid using the quadratic formula. Okay, so it saves a lot of time and effort. It does introduce a little bit of error into your calculations. And so if you want the absolute perfect, totally 100% accurate number, you would still have to use the quadratic formula. But in most cases, the error that this method introduces is small enough that it's considered acceptable, like under 5%. Okay, so you can only make these assumptions under certain conditions though. And those conditions are when the initial concentrations or partial pressures are very large and KEQ is very small. Okay, so and in that case, the change in concentration will be less than or equal to about 5% of the initial concentration. And that's why you end up being able to ignore the plus x or the minus x compared to the number it's being added or subtracted to or from. So if the initial concentrations are more than about 1,000, and this means greater than or approximately equal to 1,000 times larger than KEQ, or in other words, if they're in scientific notation, then you'd be looking for a difference between the initial concentrations and the KEQ of at least 3 orders of magnitude. That is, the exponents should be different by at least 3. That'll allow us to assume the change in concentration is really, really small relative to the initial concentration. And so in other words, we could end up assuming that something like 0.2 minus x is pretty much the same as just 0.2. And eliminating that x is often enough to eliminate the need for the quadratic formula. And here's the example with the dissociation of a weak acid. Because all organic acids are weak acids, their dissociations are equilibrium reactions, where they give up an H+ ion to water, and you end up with H3O+ and the anion of the acid. And since they are equilibrium reactions, you can come up with an equilibrium constant for the dissociation of each weak acid in water. And since those are so commonly used, but they're most commonly used in acid-base chemistry rather than general equilibrium chemistry, they're given a special name, and that name is Ka instead of KEQ. Ka, A just for acid. So we have here a weak acid, formic acid. This is the stuff that fire ants spit into you after they bite you. And being an acid, that's why it burns so much. And the formula for formic acid is HCOOH. And the book tends to write things like this as CO2H, but I tend to write it that way because that's the way organic chemists write it. Even though I'm not an organic chemist, I think it still makes sense to write it that way because it shows you what the molecule looks like and how the molecule is arranged. And it allows you to recognize at a glance what type of molecule it is. So the formic acid molecule is actually arranged like this, where you have a central carbon with a hydrogen single bonded to one side, an oxygen double bonded up above, and OH single bonded to the other side. So HCOOH. And that's why I like to write it that way, because this is much easier for you to recognize immediately as this than HCO2H would be. And so anytime you see COOH at the end of a chemical formula, you know right away that's an organic acid, and therefore it's a weak acid, but it is still an acid. And you can set up an ice table for this reaction. It's HCOOH, and it's important to remember that when you write the formula for an organic acid with COOH, it's the hydrogen at the end that's the acidic one. This hydrogen right there is the acidic one. That's the one that comes off the molecule and goes over to the water. So it's HCOOH plus H2O. H2O, remember, is a pure liquid, so you don't count that in the ice table. So that's why I put a scribble under the H2O, just so that I won't be tempted to fill it in. And then, since the problem didn't mention anything about the products being there at the start, we're going to assume that the products both have a concentration of 0. H3O plus is the hydronium ion. That's what happens when you take a proton, that is an H plus ion, and attach it to a water molecule. And this is the formate ion, HCOO minus. That's what's left when the acidic hydrogen leaves the formic acid. We're starting out with 0.250 molar concentration of formic acid, and we have nothing of either of the products. Everything here is 1-to-1. And since we're starting with no products, it's obvious the reaction's got to be going left to right. So we're going to be losing reactant. So we're going to call that change minus X. And we're going to be gaining both of the products. So we'll call that plus X for each of them. And then so at equilibrium, the formic acid will be 0.250 minus X. And the H3O plus will be X. And the HCOO minus will also be X. Now, in reactions like this, you will often, especially if you're doing it in the lab, you'll just take a pH probe and stick it in the beaker and find out what the pH is. And from the pH, you can directly get the concentration of the H3O plus at equilibrium. And once you know what that is, you know what X is, and you can fill in everything and find your equilibrium constant really easily. But if you don't know the pH of the solution, then you're going to have to work everything out. So what we've got here is we don't have the pH. So we know that the KEQ, which again, if it's a weak acid, we can also call Ka, is going to be products over reactants. Remember, the H2O is a pure liquid, so it doesn't appear in the equation. And that's going to be X times X over 0.250 minus X. And that is 1.8 times 10 to the minus 4, because that's the value the book gave us for the equilibrium constant for the dissociation of formic acid. And so to find the equilibrium constant, you've got to find X. But unfortunately, when you straighten out this equation here, X squared over 0.250 minus X equals 1.80 times 10 to the minus 4, you end up with, ultimately, X squared plus 0.00018X minus 0.00045 equals 0. And that is a quadratic equation. And you can go through that. You can use the quadratic equation if you want. A will be 1, B will be 0.00018, and C will be 0.00045. And good luck with that. But we can just make an assumption here that will make it much, much, much easier. If we assume that 0.250 minus X is about the same as 0.250, in other words, the minus X is very small compared to 0.250, then it becomes a lot easier. And we can make that assumption because 0.250 and 1.8 times 10 to the minus 4 are different by more than a factor of of 1,000. If you take 0.250 divided by 1.8 times 10 to the minus 4, the ratio between the initial concentration and the equilibrium constant, you get, oh, I did it down here actually, you get 1,389. And that, you might recognize, is greater than 1,000 by quite a bit. And so because of that, you can make that assumption. And so we're going to make that assumption. And the equation above, the x squared over 0.250 minus x becomes x squared over 0.250. And that's equal to 1.8 times 10 to the minus 4. So you just rearrange the equation. We find x squared ends up being 0.000045, and take the square root. X is 0.00671. And if you want to go back and check, you can find the KEQ using that value for x, and you will end up with 1.85 times 10 to the minus 4, which is really close to 1.80 times 10 to the minus 4. It's, in fact, close enough. Okay, and this is just about the 3 orders of magnitude. 0.250 in terms of orders of magnitude, that would be 2.50 times 10 to the minus 1, and k is 1.80 times 10 to the minus 4. That's a difference of 3 in their exponents, and that is big enough for you to make that assumption. Or you can just take the initial concentration divided by the equilibrium constant, and if it's greater than 1,000, then you can make the assumption, and it was here. Now, it's important to remember that the only x's you drop are the ones that are being added or subtracted from other numbers. The x squared, the x's that are off by themselves, like the x squared here, those have to stay because they're not, relating to anything else. So they're significant because they're on their own. But you can drop any x's that are being added or subtracted, as long as there's a difference, as long as the concentration initially is greater than the equilibrium constant by at least a factor of 1,000. Okay, there is an example here that we're going to go over, but I want to break here for the second half of the video so the halves won't be too long, and we'll pick up there in a moment.